Hi, I am going to talk about PSL2C representations of knot groups, and this is joint work with Anastasia Tsiatkova. So the goal is, given just a diagram of a knot, and we'll have a mild restriction on what types of diagrams we're talking about, I want to produce an algorithm that really showcases the geometry of hyperbolic knot complements and allows us a mechanism to, again, just based on the diagram of the knot, produce representations of the knot group, the fundamental group of the knot complement, into PSL2C. And this is going to be highly dependent on the geometry of the knot complement. So for this to be a rich discussion, I'm basically going to assume that we're talking about hyperbolic knot complements. So the knot complement has a complete finite volume hyperbolic structure. Another way of stating what I want to do is I essentially want to determine the canonical component of the character variety of the knot complement. So the character variety is essentially the quotient of all representations of the fundamental group of the knot complement to PSL2C up to conjugation. Now, technically speaking, well, we can just define the character variety is the set of all characters chi rho, such that rho is a representation from pi 1 to PSL2C, where chi rho is a character function. It takes an element gamma in the fundamental group, and it's just the trace of rho of gamma. So we can think of what we're producing through this lens as well. So some important facts: the character variety of a knot complement, or more precisely of its fundamental group, if the, if the knot complement admits a hyperbolic structure, then this character variety might have several components from an algebraic geometric point of view. For example, x times y has two components because x times y equals 0. This is a polynomial that can be written down as a product. X equals 0 is one axis and y equals 0 is the other axis. So when I say character variety, this might not be a variety, might not be irreducible in the algebraic geometric sense, but there is a favored irreducible component, a canonical component, which is one that has the character, I'll write, say, chi rho naught, of a discrete and faithful representation. This is a representation that corresponds to this lovely complete structure. So any such component has complex dimension 1. These are complex algebraic sets. And this is a fact that we're going to use in constructing our algorithm. So if we just talk about this in the lens of character varieties, then you can compute this by hand if you know a presentation for any group. You just look at all representations of your group into PSL2C, and then you do this up to conjugation. Basically, this is something you can solve for slightly nicer equations using using reduction theory. You can take resultants of polynomials. There are related varieties to the character variety. For example, the Ptolemy variety that use triangulations. And a lot of times character varieties are computed directly from the fundamental group. And there are families, infinite families of knots, usually that just vary by a twist region, so the number of twists in a region like this that have been computed. I've listed some families here: twist knots, double twist knots, several families of pretzel knots, and Cheesebro has also connected what character varieties of two-bridge knots look like in terms of fairy diagrams. So we have an idea of what a lot of these sets look like, and we do have ways to compute them when the manifold is not too complicated. And the work I'm going to present now is different than most of these methods, because these methods that I have on the slide depend either on the triangulation or are just depending on the fundamental group. And our method, although we will be talking about the Wordinger presentation, is really a method that is going to look at the diagram of the knot. So I said that there is a mild assumption, and our assumption is that our knot is taut. So the technical definition is here. The associated checkerboard surface is incompressible and boundary incompressible, and it doesn't contain a accidental parabolic. So we believe this taut condition is generic. Here's a kind of silly example of a non-taut diagram. And one way to see that this is not taut is that if we take this little arc here, then this little arc can be pushed onto the boundary of a neighborhood of the knot complement. It's known that alternating diagrams are taut. So we'll just be assuming that our diagram for our knot is taut. Okay. So I said that this algorithm is going to really depend on the geometry and really comes from the geometry. So it's based on this theorem of Thurston. So in the character variety, think of this as if we're going to be algebraic geometers. This is dimension 1, complex dimension 1. And here is a character. Just think of it as a discrete and faithful representation up to conjugation. Okay, so this is a canonical component. This has dimension 1. Thurston showed that in any neighborhood of this character, so if you like to think of things in terms of real geometry, here's Cairo, and take any neighborhood of this discrete and faithful thing, then there are infinitely many really well-behaved hyperbolic structures on the knot complement. So I want to draw some of these. So when I'm saying knot complement, I really mean S3, minus a tubular neighborhood of the knot. So here is the most nerve-wracking part of my presentation, which is I have phobia of drawing knots in public, but I guess since this is over Zoom, it shouldn't count. So hopefully that's the figure 8 knot. And I want a tubular neighborhood. So I'm just going to thicken it up a little bit. Here's my best attempt at a tubular neighborhood of the figure 8 knot. Now, the boundary is a torus. So there are really two pictures to consider. The discrete and faithful representation, sorry, the complete finite volume hyperbolic structure on this is going to lift to, well, this boundary torus, a preferred lift would be a horosphere. I'm going to take my horosphere at infinity. And then there are an infinite number of other lifts in H3. And these all lift to other horospheres. So something very vaguely like that. And there are other representations that aren't necessarily corresponding to the discrete and faithful one that will lift to a picture like this. But perhaps the more generic situation is where my boundary torus lifts to what I'm going to call a banana. So this is a banana. What do I mean by banana? Here, this is a banana with ideal endpoints here and at infinity. And we can draw in a geodesic, hyperbolic geodesic in the center of the banana and realize this banana as, in hyperbolic terms, a curve that is a surface that is equidistant to this geodesic. So other bananas, first I'll maybe draw their geodesics. So this again will lift to the boundary torus of my knot, will lift to an infinite number of bananas. I'm just drawing a few. And here kind of the generic looking bananas. This is what a curve, I keep saying curve, I mean surface, of points, all fixed distance from a geodesic look like. Okay, and I can shrink my neighborhood of a knot. I should say this is all up to homotopy. So I'm taking a nice neighborhood of the knot so I get the actual banana and not sort of a, 5-day-old banana or something tragic like that. So if I shrink the neighborhood of the knot to get closer and closer together, what I'm going to get is kind of a different level set of my banana. So if I shrunk it, maybe I'd get these skinnier bananas. They're a little bit closer to the geodesic. And in the left-hand picture, if I shrink my neighborhood, what I'm going to get is just planes, Horus spheres that are small. Okay, so for example, Thurston showed, again, this is the picture for an infinite number of points in this neighborhood here, this neighborhood here. Oh, you can't see that, I'm sorry. This neighborhood here, I think you can see my cursor, I hope so, of a discrete and faithful character. And in particular, there are an infinite number of hyperbolic structures that look like this that corresponds to Dane fillings. And the key point is that the complex dimension of a canonical component, so in this picture, this is a canonical component because it has a discrete and faithful representation or discrete and faithful character, has dimension 1. And so if I have equations that an infinite number of points satisfy, then the Zariski closure, which is this whole canonical component, has to satisfy those equations as well. Sorry, I'm going to just write this down here. I think I wrote it somewhere else, but I've forgotten where. So the point is that since the complex dimension of a canonical component is 1, we need only understand infinitely many representations. Okay, in particular, if I just understand equations that govern the Dane fillings, and if I can unify those equations, then there's a risky closure, meaning basically the equation that governs them all, governs the canonical component, will also have to satisfy these. Okay, so here's our plan. And again, I'm going to attempt to draw lucky old figure 8. So given our knot complement, that might even be worse than before. Here we go. I'm imagining I have a nice tubular neighborhood. And I'm going to pick a base point on the boundary of the knot. And if I ever need to, I'll refer to that as B. And I'm going to orient my knot. So let's say I'm going to orient it. Oh, that was terrible. There we go. Let's say I'm going to orient it going this way. Then I'll take a meridian at the knot, a meridian that respects the orientation. So here you can see that's going to go around the knot that way. And up to conjugation, well, my meridian could be anything, let's say A, B, C, D, but up to conjugation, I can assume that it's upper triangular, and I can take the off diagonal to equal 1. So I'm going to use some degrees of freedom for my conjugation to normalize my meridian of this form. And I'm going to call this matrix script M. And what am I going to do? Starting at my base point, I'm going to show you how to realize all of the Wordinger generators in terms of, I'm going to decompose them in terms of what I'm going to call peripheral arcs. So that's going to be an arc going just along the boundary torus. And then at a crossing, I'm going to hop from one component of the knot to another. So this part here, this one would be a peripheral arc. And I'm going to call those beta. And this little hop here at a crossing is a crossing arc. And I'm going to call those gammas. So hopefully you can see, even in my somewhat questionable picture, that I can find all of the Wordinger generators by doing this kind of thing. So in this picture, I can go, I really hope you can see my cursor. Here's the first meridian going that way, and I can get to another meridian by going along the boundary of the tubular neighborhood, or along the boundary torus, jumping up, and then I can go around the this little piece of the knot here just once. I don't know, I was circling so many times, so I can go around that piece and then retrace my steps, fall back down the crossing arc, go back around the peripheral arc, and end up back at B. So here, let me try to make this so you can see the whole thing. Here's a nicer picture of this. So the bottom, just imagine that as just a little snippet of my knot complement. And how do these things look in the lift? So I'm just going to draw the diagram of the lift into H3 when these are banana-looking bananas, but a similar picture exists if we're talking about horoballs or horospheres. So if I start, let's say, where do I want to start? Let's say here, then that lifts to some point on a banana. And this crossing arc here lifts to a path that goes from one banana to the next. And then maybe I traverse along the boundary torus of my knot complement, and that has to lift to something. Well, the boundary torus, it lifts to a banana, so this goes around a banana. Now again, I'm crossing, and that lifts something that connects two bananas, and then I go along my merry way again along the boundary torus. So what we want to do is essentially show that this picture, the top picture that I drew up here, is accurate. So I haven't said anything that was a lie, but I did draw these gammas, the gamma tildes, the lift of the crossing arcs, very nicely. And we want to show that we can take these to be really nice paths that go from one banana to the next. So why can, actually, let me show you this previous one. Let me just look at this one gamma. Let's look at this one. Gamma, there's a lift of gamma 1 and there's gamma 1. I drew it really nicely, but it's totally conceivable that the lift of this path does something horrible. So it could, you know, why should this lift, this green one, and hope no one listening is colorblind, and this orange one, why do they need to be different? It could be that instead of gamma tilde here going between green and orange, maybe they're the same banana. So that's the first thing that does not happen. And the second thing that does not happen is that it's also possible that gamma, instead of going straight, I've drawn it as going up a geodesic from one banana to the next. I mean, why can't it go round and through here and over there instead? So luckily, it can't do either of those things. And the reason is that we've made this assumption that the diagram is taut. So that forces our lifts of these crossing arcs to be homotopic to a, to basically be homotopic to a geodesic. So for example, my original non-taut picture was the simplest to see. Here, if I draw a gamma, this gamma, I can just homotop it onto the boundary. So that's one part of the definition of tautness that cannot happen. You cannot be homotopic to a boundary. And then this more complicated situation, you can show it doesn't occur. For example, this kind of weaving picture doesn't occur because we do have an infinite number of these lifts that we're dealing with. And all I really need to know is that this doesn't occur for an infinite number of them. But if it did, then we'd have an infinite number of these geometric structures that would be getting close to a really nice one. And so we can actually look at the length of these paths, and they kind of get stuck around this banana B here. And you can show that these paths would get arbitrarily long, but that can't happen. Okay, so either way, our taut condition shows us that this picture here that I originally drew is the way it happens. You can't do any of the weaving, and these bananas that the crossing arcs gamma, they start on one banana and they have to end on a different banana. Okay. So what do we learn from this? The consequence is that if I draw a path on top of the knot, meaning a path that's a sequence of these peripheral paths, peripheral arcs and crossing arcs, that I can draw a path like that where the lift looks like paths on bananas followed by paths from bananas to bananas. So in the generic case, this figure 8 knot complement generically will lift to a bunch of these type bananas. Here, just a few bananas. And how do I follow my path around the knot? If I start here, that corresponds to starting on, say, that banana. I go a little bit on my peripheral path. Maybe I go here. And then I do a crossing. Call that one orange. That corresponds to connecting up there. My geodesics are not very geodesic looking, I'm sorry. Maybe that was a little longer. And then what do I do next? I do a little peripheral bit. Then that's on a banana. Then I do a crossing bit, and that lifts to a geodesic, which joins this ideal point of a banana with an ideal point of another banana. So my orange geodesic goes, if you can imagine the geodesic starting here and then intersecting at that endpoint, then it's going to go all the way through down to there, and it'll hit the banana there. So something like that. Okay, and you can, the other observation is that if you take a smaller and smaller neighborhood of the knot, notice that up here, these two adjacent crossing arcs, right, they're only differ by a little peripheral bit in between. So that's the in-between peripheral bit right there. They join at that same ideal point of the banana. So I'm going to call these ideal points where the crossing geodesics, if you will, get closer and closer to as you take smaller and smaller neighborhoods, the preferred ideal points. So when I take a path along the knot, I can do it as a sequence of peripheral paths, which lift to paths along a banana, followed by a crossing arc, and that I can take to be a geodesic, part of a geodesic that goes from one banana to another banana. And then I do a little peripheral bit that's on the banana. And then the next bit is another crossing arc. And if I extend these all the way to the ideal boundary, these two will share an endpoint. And this one will share an endpoint with the next one that came along. So the notation that I'll use is just like the previous slide. These crossing arcs I'll call gamma, and the lifts I'll call gamma tilde, and these peripheral pieces I'll call beta, and lift of that I'll call beta tilde. Now at this point, I could, in a very abstract way, start writing down my representation, because in order to write down a representation of a knot complement, I just need the Wordinger generators. And the Wordinger generators, I can realize them in this way. So for example, here, if I start here, go up that beta, up that gamma, around that beta, cross over to gamma, I can do a little bit of a meridian. Now it depends on the orientation of the knot, so I'll just draw it vaguely like that. And then go back down that gamma, back around that beta, back down that gamma, back around that beta. And if this is my base point B, I've now represented my Wordinger generator as a sequence of these betas and gammas. And so I can trace the transformation of H3 that does that, the isometry of H3, because this isometry, I can understand it fixes this banana. This isometry takes this point to this point. And because when the bananas when I take smaller and smaller neighborhoods, I take concentric bananas, that actually gives me even more information. The preferred ideal point here at infinity must go to that ideal point there. I know a lot about this isometry. I'll get back to that. Anyway, it's uniquely determined. And then I could follow with this one and with that one. Okay, but it's very important that the isometries I get really depend on which bananas we're talking about. So it really depends on this lift of my base point, B tilde. Okay, so for example, this first beta would lift to a beta tilde here on this very particular banana. And then this next beta, which is the lift of this one, is actually lying on a different banana. So even though abstractly we know how to decompose our path, then it really depends on exactly where these bananas live in H3. Okay, so we're going to get back to that and show that we can figure all that out in a very organized way. The first thing we need to be careful about when I tell you that I'm constructing a path using peripheral pieces and crossing pieces is that we have to take some care with the peripheral pieces. So if you imagine this little bit of my thickened knot, I should have mentioned up here, whoops. I should have mentioned up here that in order to control the chaos, whenever I do the series of peripheral arcs and crossing arcs, starting at my base point B, I'm going to, whenever I see a crossing, I'm going to stop at a point directly below the crossing. And I'm always going to take gamma to a point on the underside of the crossing. And then this peripheral piece will go around and end up, since this is curving underneath, it'll have to end up actually on the underside of the crossing. And this gamma will actually go from the underside to the overside. So this way I can control exactly where my endpoints are. But if you see from this gamma, if I stop here, I could go around kind of on the right side, or I could go around on the left side. And so we need to take some care in how we choose it. So perhaps it's better seen on this picture. Imagine that this is a little piece of my thickened knot, then this would be a piece where the other part of the knot is coming in down here. Okay, so the pretty computer drawn image is an overcrossing on this side. So I put my base point down below, and in this picture, the next piece would be coming up above. And so I put my next base point up above. So there are really two choices for how I can get from down here to up there, staying on the knot without unduly curving around. And I'm going to call them the left choice and the right choice. So here's the orientation of the knot. So with that orientation, this one is on the right and that one is on the left. And there are a few different scenarios to entertain. There's this one where you go from an overcrossing to an undercrossing. You could go from undercrossing to an overcrossing, or it could be a non-alternating knot section. But either way, you can see, in this case, for example, if I do the left side followed by the right side inverse, then I end up with a meridian going around in the correct orientation. If you reverse the picture so that this was starting an undercrossing and going to an overcrossing, the exponent on the meridian would be the opposite. So we have a controlled way to encode the difference between the left and the right, but we do know that those two choices will be different. Okay, so if we step back, what do we have? We have the building blocks of a representation. I've picked a base point on the knot. I want to make a Wordinger generator, see where it goes in terms of matrices that represent isometries of H3. And I'm going to do that by doing a little peripheral piece on the knot, a peripheral arc. Then I'm going to jump up a crossing by a crossing arc, do a peripheral, do a crossing. And once I get to the edge of the knot I want for the ith edge for the ith Wordinger generator, then I'll do a little meridional loop around there and then just completely reverse. So I can write my knot, if I consider that little meridional loop as a peripheral piece, it does stay on the periphery of the knot, then I can write the associated element of PSL2C as a sequence of peripheral pieces and crossing pieces. So the P for the peripheral piece and the C for the crossing piece. Now, these pieces really, really highly depend on which banana you're on at that portion of your journey. But one thing we do know is I picked at the very beginning, I picked my favorite lift for the meridian M1, 0, M inverse. And that fixes a particular banana, I'll call it B naught. And that banana has endpoints infinity and -1 over M minus M inverse. Okay, so that is my favorite of all bananas. And this is fine too if it's if M equals ±1, then I naught is just infinity as well. So that's fine. This takes care of that scenario too. And the observation is that we can do a deck transformation of our of hyperbolic space. And in our deck transformation, I can take, this is B naught, my favorite banana. And over here is just some lowly banana B. And in my deck transformation, if I have a little peripheral piece here, beta tilde, I can find a deck transformation that preserves all the bananas, that takes B to B naught. And so my beta tilde will be conjugate to something on beta naught, on B naught, I'm sorry. And that means it'll be conjugate to an element that fixes B naught. And in particular, it's going to have to fix infinity. It's supposed to look like infinity and I naught. Another way to say that is that my beta tilde, that's my lift of some peripheral piece, it's going to be conjugate to an arc here on this banana. And an arc on this banana has to commute with the meridional arc. That's my favorite of all time arc on this banana. And so we can write that a P matrix, that's the transformation that corresponds to this little peripheral piece, is going to be conjugate to a matrix that corresponds to this little journey. And that matrix, which I'm going to call calligraphy P, must commute with M. So infinity has to go to infinity. That's why there's a 0 here. And so it has to have this form, V, U, 0, V inverse. And commuting with M, we can either write it in this matrix equation or in terms of the entries. Okay, similarly, what's going on with the C matrices? I want to argue a similar thing. I have a favorite C matrix, which is the one that takes my favorite banana, B naught. That's that one that the meridian lies on, to my second favorite banana, which has the preferred ideal point at 0. So that would look like something like this. That would be the lift of, that would be my favorite type of gamma. But, you know, an everyday gamma might not look as lovely. It's just going to go from one banana to another. And it's going to be part of a path, a geodesic path that connects preferred endpoint to preferred endpoint. So this geodesic, it'll pierce through the banana, say here, and then it'll go over and pierce that banana there. And so this would be a bad, well, I mean, it's perfectly lovely, but a not as useful lift of a crossing arc gamma. But we can find a deck transformation that preserves bananas that takes this banana to the best banana and this banana to the second best banana. So my C matrix, which is the matrix representing the isometry going from here to here, kind of along the geodesic, is going to be conjugate to the C matrix, which I'm going to call script C, which goes along this geodesic from this point to this point. And again, we have a little bit more information than just the fact that it goes along this vertical geodesic, in this case, from this point on the banana to this point on the banana, because I can shrink my neighborhood of the knot and it still does the same thing, but for nested bananas. So in particular, infinity goes to 0, this intersection point goes to this intersection point, and this is enough to see that this C matrix, that any C matrix has to be conjugate to one exactly of this form. And the little c is really encoding kind of the shape of the bananas, or this, you can think of it as kind of this fixed distance, or even you could associate little c to this midpoint between the two piercings of the bananas. That's kind of what little c is encoding. Okay, so at this point we've got our path along the top of the knot decomposed into peripheral pieces and crossing pieces, and we've got a nice form that we know each peripheral piece is conjugate to and each crossing piece is conjugate to. Okay, so now let's just put this together and get ourselves a representation. Okay, so here is my journey along my knot. I go across little pieces of my thickened knot. So first, I'm going to fix a base point B on top of the knot. And then let's say this is the ith edge of the knot. I want to get over to the ith edge on the top of the knot, do my Wordinger little generator around the ith edge, and then retreat. So what do? I'm going to take one side of the path over to here and go down with a crossing. And then I'm going to go over for the peripheral. I'm going to go down with a crossing. And then I'm going to use a peripheral. I haven't written the orientation, but the knot is oriented, so I have a correct choice of orientation there. And then I'm going to retreat back along the peripheral, back along the crossing, back along the peripheral. Okay, so row of this ith Wordinger generator in this case would look like, would come from a lift of this, let me call it beta 1, beta 2, and here I have gamma 1 and gamma 2, And I'm going to call this little, I'm going to call this little meridian there mu2. So in this case, I'm looking at the path that goes beta 1, gamma 1, beta 2, gamma 2, mu 2, gamma 2 inverse, beta 2 inverse, gamma 1 inverse, beta 1 inverse. Okay, and all of this whole path, which down here I've written as I've bunched these pieces together, you can see that it's a path along the top of the knot, a little meridian, and then the inverse of the path along the top of the knot. And each of these lifts to a P matrix, say P1, a C1, P2, a C2, maybe M2. And here we have to be careful. This is C2 inverse, you'd want to say, but they all really, really depend on the base points. So maybe it's better to call it prime. B2 inverse prime, C1 inverse prime, and B1 inverse prime. Okay, and I'm using the prime because this is going to be conjugate to the C2 inverse matrix, but the actual matrix that's using here is different because this path goes along a sequence of bananas and it doesn't retreat along the sequence of bananas. So P1 is a peripheral on banana 1 that goes to via C1. So P1, oops. Let me make my, maybe this is beta 1 tilde, and then C1 will come down to another banana here, and then beta 2 tilde will then be followed by gamma 2 tilde. This was gamma 1 tilde. Okay, and now we're on the third banana. And now we do the mu, and that lifts here. I'll call it mu 2 tilde to a path on the banana. And then what do we do next? Next, we go backwards along gamma 2. But what does that lift to? That just lifts to another orange thing, geodesic from banana banana. So this is a lift of gamma 2 inverse. And then we continue in the same way. We get another lift of beta 2 inverse. And then we do a geodesic gamma 1 tilde inverse to another banana. And finally, beta 1 tilde inverse. And so, for example, this geodesic that corresponds to retreating along gamma 1 is joining different bananas than this one. But the important thing is that they will still be conjugate. Their normal forms will coincide up to, since they're inverses, up to the inverse sign, but the actual matrices won't because they're connecting different bananas. Okay. So I think I wrote all of this on the other slide, although in case you're looking here, I really want to note that these are actually different matrices because of the different lifts. Okay. I wanted to say something else. Let me check. Okay, I wanted to say just a remark about the left and the right sides. So I said that there's an ambiguity in the choice, and it's actually something you don't really have to worry about. So if you allow me to write my knot like this, let's say that I start here with my base point B, and I want to go around this this edge to get my Wordinger generator. Then the path that I need to take to get over there, if I know I'm going to take the path going like this, and then go around and then retreat along that path, then that actually specifies which side I'm going to go on. So here I would go around this side to make the leap, and here I would go around the other side to make the leap. So here, if this goes this way, I would take the right side, and here I drew it pretty badly. Let me retreat. Okay, so here I take the right side if it's that way. I have my preferred base point, which is at the top of this strand. And then since I know I'm going over this way, then if that's the direction, then there I'm actually going to take the left side. And again, here I'm going to take this side. So I'm just arbitrarily assigning directions to the knot. That would be left. And then I jump off. So you can see that in this way, actually the choice of the path on top of the knot determines left or right. Peripheral. Okay, so the left or right matrices are determined. I can take a path on the top of the knot, peripheral crossing, do a little loop and retreat and get my Wordinger generators, except these P and C matrices are horrendous. How could you ever figure out what they are? Well, the magic is that since we know what they're conjugate to, and because the process of replacing, say, a P matrix by its preferred conjugate, and then replacing the next C matrix by its preferred conjugate is basically a change of base point. If I want to move this little P piece, over to here, there's my base point. The corresponding lift, if B lifts to its preferred lift, changing this to pretend it's over there, kind of retreating, that conjugation. See, it's a video. I wish I could have deleted that. It didn't sound good. Let me say this again. So I want to replace the matrix corresponding here with the preferred one. But then I want to next in line replace this little crossing one by its preferred one. This is essentially just changing the base point. But since these are right next to each other, if I change this base point to a preferred one and follow up by changing this base point to a preferred one, there's a huge amount of cancellation. And if you work the algebra out, it amounts to, so if I write my Wordinger generator as doing the path on the top of the knot A, convert it into matrix, do the meridian around the ith strand of the knot, or sorry, the ith edge of the knot, and do that path in reverse. And again, this is not the same, not literally A inverse matrix. It corresponds to different lifts. But if I matricify the the P and C's corresponding to the retreating path, then what I get is a sequence of matrices here where I want to put primes here because these are correspond to different lifts. Okay, well, when I normalize so that each of these matrices looks like their normal form, which for the P's are elements along my favorite banana. So a P matrix corresponds to something along my favorite banana B naught. And then my favorite C matrix corresponds to one from that banana down to a banana with preferred endpoint at 0. When I simultaneously conjugate, it has the effect of getting the nice matrices we like, but just reversing the order. So I get all of these nice normal form matrices in reversed order. So what does the Wordinger generator look like if I know I'm going to have to take a path beta 1, gamma 1, beta 2, gamma 2, and then go around the ith edge and then retreat, then I can just read it off like this. Just go the other direction. The normal form of the beta 1, normal form of the gamma 1, and so on. And then these are then literally the inverse matrices because I'm no longer looking at particular lifts. I'm looking at what I deemed the nicest possible matrix that is conjugate to. Okay, so what do? We have an oriented taut diagram with a preferred base point. I pick a matrix for my meridian. For each side of each thickened arc, I assign one of these normalized peripheral matrices. And for each crossing, I assign one of these normalized crossing matrices. Okay, now what needs to be true? I've already talked about the fact that the left and the right edge equations have to be related by a power of the meridian because we're just curving around one way or another. And because these normalized matrices sit on the banana that naturally is associated to M, then they have to commute. So in other words, this is the M banana. The M matrix fixes the banana, so it corresponds to a little arc on the banana. And the normalization, what I did was normalize it so that this exact banana, which had that I naught value in infinity, is the one that my P lives on. So since they both live on the same banana, associated to that geodesic, they have to commute. Okay, now the one I didn't talk about are what I call the region equations. Now imagine that I talked about choosing a path to make a Wordinger generator that goes to the ith, oops, I don't want black, that goes to the ith arc, ith edge and around, but I could choose several paths. For example, let's just say I start here. I could go around this way to there, or I could go something like this. Either one of those would end up at the same edge of my diagram, and my representation better not depend on my choice. So another way to say that is, instead of saying that these two paths should be the same, it's equivalent to saying that any path, peripheral crossing, that goes around a region like this, right? There's nothing in the between here, must be, well, it's homotopically trivial, right? So the matrix I get better be the identity matrix. And here, I don't think I was consistent enough. I tried to use 3 equal signs because there's the plus or minus. We're talking about PSL2C. So I'm going to call a region equation any sequence peripheral crossing around one of these regions of the diagram. And they always need to give you 0, the identity. One thing that I haven't brought up is that we are going to have to pay attention to the direction of the knot, but I'll be more precise about that when I give you an example. Okay, so what is the theorem? The theorem is that because this construction holds true, because these matrices work for all, say, Dane fillings, and there are an infinite number of Dane fillings on a canonical component, there's a risky dense set, then this construction has to work, has to give us the equations for that entire set, the entire canonical component. So all geometric representations, by that I mean those corresponding to a canonical component, from the knot group to PSL2C, we can define them by defining the Wordinger generators in the manner I talked about. You do an A path, which goes from the base point on the top of the knot to the ith edge, you go around the ith edge, and then you retreat. And so that path corresponds to peripheral pieces and crossing pieces. And this script A is that path written backwards in terms of the nice normal form for it. Okay, so we have AM, A inverse for our Wordinger generator. And we know that for any geometric representation, those edge equations, the left and the right, coinciding with a little twist, the fact that going around a region in the diagram is null homotopic, so the corresponding matrices are the identity, and the fact that the peripheral pieces commute with the meridian pieces because they're normalized to live on the same banana. So the commuting equations all have to be satisfied. That's what I've been yammering on about for God knows how many minutes now. But conversely, if we just blindly label all of the edges left and right with those p-type matrices, all crossings with c-type matrices, and if we define rho of a Wordinger generator to be the AM A inverse, you know, for any path that you take to get to the ith edge, then if you make sure the edge, region, and commuting equations are satisfied, you will always get a representation. And that's easy to check. You can just check that doing this process always satisfies the Wordinger relations at a crossing, and it easily does. So the geometric representations all look like this. Oops. Okay, so a couple of remarks. There are some ways to beautify this a little bit. You can look at the geometry, and I will spare you, but if you take a two-gon, trying to draw a two-gon without getting too much hand on there. If you take a two-gon like this, then if I want to label my two-gon, I label it with crossing. There's another crossing. And if I do the interior, peripheral 1, peripheral 2, then we would need the equation C1, P1, C2, P2 is the identity. And it turns out that what has to happen is that these two must be the same. And these P's must be the identity for two-gons. So it simplifies the two-gon calculation quite a bit. The other thing is that we can, we can use this two-gon situation if I have a knot with a large twist region, and I can simplify the twist region. Oh my goodness, I wanted to do it in black and I'm set on it for some reason, so let's try it. Okay, so I can do a large twist region, which I've just discovered right now. Apparently I can only draw in a particular manner. So forgive me, I'm going to draw it like this. There's a nice twist region. And we know that all of these are then the same, and these are all identities. And so you can rewrite this portion of the equations nice. So it does simplify the situation for large twist regions. The other thing I wanted to mention is that you can relate the entries of our matrices. So if you look over here, the V's are the diagonal portion of the peripherals and the U is the off diagonal. So you can, if you're labeling consecutive pieces of consecutive edges, then you can relate the U's and V's from the peripheral and the C's from the crossing to shape parameters. So I'm going to make an attempt to draw what I mean. So if I take this and okay, so this is a pentagon. Then how do I go around this pentagon in my scheme? I go around by I have these little crossings, and I have these peripheral pieces. And how do they lift? This is a null homotopic loop. So it lifts, I'm going to have 5 bananas. And please forgive me, these are going to look pretty rough. Okay, there are my 5 bananas. And my crossing pieces maybe look like this. And they're joined together by peripheral pieces. But the crossings lie on geodesics. So if I just erase my bananas, I have a nice little picture in terms of these geodesics. Oh, I didn't know it could do that. Let me try to make it look so ugly that it doesn't want to make my picture prettier. Okay, so use your imagination that these look like, ooh, like geodesics, please. 1, 2, 3, 4. Good, one more. And you can associate the cross ratio of these Z's are the ideal points. So these are the Z's in order. You can associate the cross ratio of 4 consecutive Z's to a formula that involves the U's, V's, and C's. So you can think of the equations in terms of these shape parameters. Okay, the last thing I want to do is just to show you with the figure 8. I'm not going to write down the actual equations, but just to make sure that it's clear how this labeling goes. So first, I need to make sure I've got an orientation of the knot. So I'm going to orient it all the way around. And then I'm going to use the fact that I have 2 two-gons to make life easier. So that means that these side peripheral labels are the identity, and this crossing label and that crossing label are the same. So I'm going to label those as C2 and C2, because down here I also have a two-gon, and these interiors are I, and I'm going to label that as C1 and C1. And let me make my C1 definitely look like a 1 so we don't get confused. Okay, and now I need to label my other peripheral pieces, and I'll label this one P1. Don't know why I'm having trouble with ones. Let me try again. P1. Oh, I should have started over here. We can use the edge equations here to realize that this right-hand side is M and this side is M. And the same edge equations tell us this is M inverse and this is M inverse. But in fact, we don't actually need to do the region that is the outside of the knot. The fact that that is null homotopic will follow from the other ones. So I'm just going to delete that. Okay, so I've got all my two-gons and their outsides taken care of. Then I'll label that one P1, and the edge equation tells me that this is MP1. If I label this one P2, then the edge equation tells me this one is MP2. And so all I have to do is label this and this. So I'll label this one P3 and I'll label this one P4. Okay, I've essentially used the edge equations already. And so all my representations will be determined by the fact that P1 M equals MP1. I'm going to say that more concisely. I'll say PIM equals MPI. And I'm using the M from before in the format of the PI before. And now I have these three regions to worry about. This one. So for this one, that region, what do I do? Well, I'm going to pick a starting point. Let's start here. And here I'm going to have P1, my orientation agrees. So it's P1. And then I cross at C1. And then I do M, but with the opposite orientation. So that's M inverse. And then I cross at C1 again. And then I do P2. Sorry, that's a P3, isn't it? And then I cross at a C2. And then I'm back where I started. So that's the totality of the green region. And now we just have two other ones. Let's do this yellow region here. For the yellow region, again, I'll pick a starting point. Oops. How about I start right here? So I get M inverse because M inverse agrees with the direction. C2. MP2, but I'm going the wrong way. So MP2 inverse, and then C1, and then MP1 inverse. And so then, oh, and then C, and then I almost forgot about C2. And then I'm back where I started. And then finally, oops, I'm clicking the wrong device, get this one. And this one is very similar. If I start here, what do I get? I get right in black. I get P4, C1, M inverse, C1, P2, C2. And so these equations, I have 4 P's, so they're 4 commuting matrix equations, and 3 of these, and these all are equal to plus or minus the identity. Satisfying these 3 matrix equations and these 4 commuting matrix equations entirely tells us what the variables are for our representation. Okay, I'm going to stop there. Thanks, everybody. Bye.